In this video, we're going to zoom in on the big data in the modern world. We're going to look at today's computing benefits, today's computing challenges, common problems that we have today, and how to solve them. Today's computing benefits are many. We're now sitting on monstrous amounts of CPU and RAM thanks to Moore's law. All of our computers are jam-packed with these resources, and unlike 10 years ago, these are no longer the bottlenecks. Storage is also incredibly cheap, so we have organizations buying more and more disk, storing more and more information, and we need some way to leverage that. We're also standing on the backs of giants with regards to distributed systems design. We have the NoSQL and cloud movements that have contributed heavily to this, and we have systems that are now very redundant and fault tolerant. We also have open source software and commodity hardware. The open source movement started about 20 years ago, and it's also very mature, with many of the major products we see out there in the form of open source. Commodity hardware is also all over the place. Not only has hardware gotten a whole lot cheaper, but many organizations, through their aggressive upgrade cycles, now find that they have hardware lying about, and they want some way to take advantage of that. Public cloud options are now also very mature. We have companies like Amazon providing Amazon Web Services, and this is a great place to do big data processing. Tom White, in his excellent book, Hadoop, the Definitive Guide, says that network bandwidth is the most precious resource in a data center. This is probably the biggest computing challenge that we see. Many organizations started out with a centralized disk store and then had many processing nodes pulling that data down and processing it locally. We gave this example in another slide with the SETI at Home project. The problem is all of these local machines probably use cost-effective mechanical disk. This means that each local machine is slow, and so is that central data store. The other thing that we see running very, very slow in the modern data center is the network bandwidth. There simply isn't enough bandwidth to move all these bits around back and forth between a central data store. We want some way to minimize this movement of data. Hadoop takes an approach that's very similar to two concepts that we see with disk I/O. Cost-effective disks, as we know, are still mechanical and not very fast. Along with these disks, we have various disk write and read options that we can leverage. If we cracked open the case of a 3.5-inch drive in your server, it would look something like this. These platters here on the outside store the information, and this disk head right here moves back and forth on the disk, reading and writing that information. There's two ways to do read and write onto disk: sequential or streaming, and random over here on the right. With sequential, we lay the bits out on the disk in a sequential fashion so that the disk head moves through smoothly to read all the information. Whenever possible, we try to leverage sequential streaming to get the best disk I/O. Random over here on the right takes a different approach. It actually breaks the information up and spreads it around on the disk. This is often what we'll see in database, with various tables being written out to various parts of the disk. This allows databases to store each table in a streaming fashion, and yet come back and read the information from multiple tables, for example, in a join. This is not the fastest way to do disk I/O because the disk head has to hop around and read these various bits. With regards to not only mechanical but also SSD drives, we also see users doing striping and mirroring, and we're going to zoom in on what these concepts are. In both of these cases, we start out with a single file here in the middle. With regards to striping, we want to take this file and cut it up into many pieces, moving each piece out to, say, one of 4 disks. When we come back to read from these disks now, we can have 4 disk heads, each reading 1/4 of the file, perhaps reading it back in about 1/4 of the overall time. With mirroring, we still start out with a single file, but we just make a second copy of it, and we move that entire whole copy over to 2 or more disks. Striping's big benefit is that it provides increased speed. Every time we add a disk, we now have another head being able to read these files back. Mirroring provides us something else called redundancy or durability. For example, here, if we lose an entire disk, we still have an entire copy of the file on another disk. A lot of organizations use striping and mirroring together. Striping is commonly known as RAID 0 and mirroring is known as RAID 1. RAID stands for Redundant Array of Independent Disks, and that's what we have here. 4 disks on this side and another 4 disks on this side. Here we're showing that we striped a file across 4 disks and then mirrored those entire 4 disks on another set of disks. This gives us both speed and redundancy. Just remember that this is the approach that Hadoop takes on a larger scale, providing both striping and mirroring throughout the cluster. Today's big data problems essentially break down into 2 areas, technical and human. On the technical side, we have a lot of problems that are parallelizable. We have things that we can do in parallel, and we can leverage commodity hardware, perhaps running on open source software, as we see with Hadoop, to cost effectively and very quickly tackle these problems. A lot of organizations cut their big data teeth with recommendation engines. The average company reports that they can get about a 3 to 5% bump in their retail website sales simply by implementing a recommendation engine. And technologies like Hadoop make that as easy as a one-person, one-week project. Doing things like index building to go back and search vast amounts of information. We see this with Google as well as some companies that just have a ton of information inside their organization that they need to make accessible to users. Building an index is a separate process that goes through and perhaps indexes every word in a document and ranks the documents in relation to each other, much the same way that Google works when you come back to do a search. A lot of companies do extensive log analysis, finding things like click paths, like root cause analysis of failures and so forth in large data centers. On the human side, we have an issue that's commonly overlooked, but is very, very important when we start doing big data analysis. Big data exposes information that we think is personal. One of the examples I always like to call out here is Target's pregnant teen situation. In February of 2012, Forbes magazine wrote this great online article that you'll find in the appendix. Forbes highlighted how Target had an issue with one of their local retail stores. What happened is that a father called up the local retail store in rage that Target had sent his innocent 16-year-old daughter a bunch of coupons for baby-related items. In the flyer, Target made a reference that the daughter was probably due in 6 months and congratulated her on her baby. Target really didn't know how old the girl was. They were just following her point-of-sale Super Saver card that showed all the items that she purchased. The manager of the local Target really had no idea what was going on when the father called up his store. He made a note to call the person back in 2 weeks. So when he called the girl's father back in 2 weeks, he was quite surprised to find out that the father was actually apologizing. The father said that he and his daughter had a talk and actually realized that she was due and almost down to the week that Target had made reference to in the flyer. One might think, of course, Target was just simply following what the girl was ordering in her cart, and when they found out she was ordering baby diapers and formula and things like that, it's kind of a no-brainer. But it was more complicated than that. What Target was actually tracking was a whole bunch of buying patterns across pregnant women. What they did is look for when women started buying baby items and then trace back 6 months into their purchases and start looking for changes in buying patterns. What they found, for example, is that a lot of women in their first trimester switch from scented to unscented hand lotion because the scented lotion makes them nauseous. Things like this that big data finds wouldn't be on the forefront of any marketer's mind, but this is buried in the data, and the data doesn't lie. Target had an excellent solution to this problem of maybe freaking out their users. What they did is when they found a woman matching the buying patterns indicating she would be delivering in a few months, they instead just randomly mixed in a bunch of baby-related coupons into her flyer. They never made a reference to the woman being pregnant. It just so happened that a lot of the items that she was looking at were now on sale. Another unfortunate example that I have to give is the NSA and the huge backlash that they're experiencing with regards to their monitoring of user information. Regardless of how you feel about Edward Snowden, the truth is that the NSA is monitoring us all at a level that probably freaks out 80+% of Americans. When you, your division, or your organization gets into big data-related problems, don't underestimate the human side. Take lessons from Target and the NSA and look at how things can go wrong as well as how you can fix them. Some of the solutions that we have for big data problems are parallelizable and everything else. Anything that can be broken down into a bunch of individual chunks is an excellent choice to do MapReduce and Hadoop processing on. If, for example, I can take a single file or set of files, break it up into a whole bunch of pieces, and distribute those pieces to a whole bunch of nodes, as we saw with the striping example, I can leverage this cheap and effective disk storage across many heads to process a file all in parallel. At its core, that's exactly how MapReduce works, and we'll investigate this in another chapter. Again, any data that can be analyzed in pieces. If we can break a record set up and put it across many, many disk heads, we can analyze it in a parallelizable fashion. Everything else typically falls into about 5 to 10% of the data analysis out there. There are things that do not work well with MapReduce. For example, anything that is computationally intensive. In other slides, we'll see that by peppering data out to the edge nodes, the MapReduce paradigm avoids all of this disk I/O and network I/O that is so problematic in data centers these days. However, if you have anything that's computationally intensive, you should still look at solutions from companies like Cray and IBM. Both of these companies have an excellent array of supercomputers that deal well with these computationally intensive problems. Anything regarding graph analysis, for example, resource flows and social graphs, where we have individual nodes that cannot represent the whole picture of the data. In this case, you might want to look at other solutions, for example, the Crays and IBMs mentioned earlier. In this chapter, we looked at big data in the modern world, we discussed the benefits and challenges, the common problems that we have today, and the solutions that exist. This chapter is essentially laying the groundwork for describing the Hadoop distributed file system and the MapReduce paradigm.